Okay, so implicit differentiation. Hit pause, copy the lesson objective down. Once you're done, hit play, and we're going to talk about differentiating implicitly. Right, so differentiation. Up till now, we've differentiated explicitly. So we've always been given y in terms of x. Y is equal to a function in terms of x, which allows us to differentiate then with respect to x. Sometimes it's not always possible, and so we have to differentiate what's called implicitly. We have to differentiate the terms as they stand. In order to do that, we use the chain rule. The chain rule features prominently in this, and in this form. So if we have d over dx, we're going to differentiate this function y with respect to x. What we do is we use a chain rule and we differentiate with respect to y, the function of y. But because of the chain rule, we have to then multiply that by dy over dx. As you can see, the dy is cancelled, so you really have d over dx, a function of y. It's written like this: d over dx, the function of y, which is equal to, if we differentiate that with respect to y, we get f dash y dy over dx. And that's what forms the basis of what we're going to be looking at today. Something for you to note, where we want to do d over dx of y to the power of n, so I'll put some brackets around that. That's going to be equal to the power n times y to the n minus 1, and then we just bung in our dy over dx next to it. Okay, so two things for you to make a note of. Once you've done that, we're going to look at an example. These things are always clearer with an example. So hit pause, copy that down. When you're ready, hit play again. Okay, so let's have a look at this example. Differentiate the following equation explicitly. So let's take our equation. We got y cubed is equal to 3x squared. So to differentiate it, we want to differentiate it with respect to x. So we've got d over dx of y cubed here is equal to d over dx of 3x squared. Okay, so if we consider the left hand side, what we said, in order to differentiate that, what we do is we differentiate with respect to y. So we do d over dy of y cubed, and that's going to be multiplied by dy over dx. Okay, remember what we said about the y's cancelling? That's equal to, if I differentiate the right hand side, that gives me 6x. Nice and simple. Now if I come back to the left hand side, differentiating y cubed with respect to y gives me 3y squared times that dy over dx, which we have to put there, and that's equal to 6x. So that means then that dy over dx, dividing both sides by 3y squared, is equal to 6x over 3y squared. And that's implicit differentiation. So hit pause, copy the example down. When you're ready, hit play, and we'll look at another example then. So this example, we've got a circle with the equation x squared plus y squared equals 25 sketched out, and we've got to find a gradient when x is equal to 4. So let's write out our equation. X squared plus y squared is equal to 25. So we're going to differentiate that. So d over dx of x squared plus d over dx of y squared is equal to d over dx of 25. Now this line is not normally written. We tend to move on to the next line straight away. So if we differentiate x squared with respect to x, we get 2x plus, I'm going to write this out this time, d over dy of y squared times dy over dx. Although we don't, we tend to just go into the differentiation straight away. But for now, we'll do it like this. And if we differentiate a constant, we get 0. So 2x plus differentiating with respect to y, we get 2y dy by dx is equal to 0. And if we subtract 2x from both sides, so we've got 2y dy by dx is equal to minus 2x. So dy by dx is equal to minus 2x divided by 2y. The 2's cancel, so dy by dx, the gradient, is equal to minus x over y. So we've got our gradient. Now we've got to find the gradient when x is equal to 4. So it's a bit of a naughty question. It's a good thing they've given us a sketch. When x equals to 4, we've got two solutions. So here, our coordinates are 4, 3, and below our coordinates are 4, minus 3. So we've got to find the gradient at 2 points. I'll just change my pen to a different color, make it easier, blue. Right. I'll tell you what, I won't say when. Instead, I'll say at coordinates. At coordinates 4, 3. dy by dx is going to be equal to minus x over y, which is equal to minus 4 over 3. And so that's one set of results. So our gradient at that point at coordinates 4 minus 3, the gradient, which we know is minus x over y, is equal to, sub in the figures, 4 minus 4 over minus 3, so it's just 4 over 3. And that's job done. Good. So it's quite powerful, it's quite useful, very helpful sometimes to be able to differentiate implicitly as it is, as it stands, we differentiate it. Hit pause, copy the example down. When you're ready, hit play again and we'll look at another example. Okay, let's have a look at this example then. Differentiate in terms of x and y. As we've said, it's not always easy to make it y is equal to. So we've got this new tool which we can use to differentiate as it stands implicitly. So we've got x cubed plus x plus y cubed plus 3y equals 6. So this time we're going to differentiate without having to write d over dx for each term. If I differentiate with respect to x cubed, I get 3x squared. Nice and simple. Differentiate x, I get 1. Plus, if I differentiate y cubed with respect to x, remember I differentiate with respect to y, so I write 3y squared, but I've got to bung my dy by dx next to it. Plus, if I differentiate 3y with respect to y, I get 3. I've got to remember I've got to put my dy by dx next to it. It's equal to differentiate a constant, you get 0. So now I've got to simplify in order to get my my gradient, dy by dx. So let's do that. I can factorize here. At the same time, I'm going to move my 3x squared plus 1 from the left to the right hand side. So here I've got 3y squared plus 3 dy by dx is equal to, these two terms are positive on this side, so they'll be negative, minus 3x squared minus 1. That means my dy by dx is equal to, I'm going to divide everything by 3y squared plus 3. Gives me minus 3x squared minus 1 all over 3y squared plus 3. That's job done. if you feel the, I'm happy with that. If you feel the urge to tidy up, you could say you have minus 3x squared plus 1 all over 3 brackets y squared plus 1. But that's job done. Okay, so hit pause, copy the notes down, or copy the example down rather. Once you've done, we'll have a look at one more example. Okay, so we've got a different challenge here. We've got, given that 4xy squared plus x squared over y is equal to 10, find the gradient at this point. So let's take our function. We got 4xy squared plus 6x squared divided by y is equal to 10. Now in order to differentiate this, I'm going to have to call in the product rule for these, 4x times y squared, and then the quotient rule for these. So it's quite a challenge. What we're going to do is we're going to try and differentiate implicitly, and we're going to try not to write assign u and v. Now, product rule is given by dy by dx is equal to, remember, u dv by dx plus v du by dx. So let's apply that to this part of the equation first. So if that 4x is u, we just write 4x, and that's v, so we've got to differentiate that. That's going to be 2y dy by dx plus, this time I'm going to write v, which is the y squared, times differentiate the 4x, it's just 4. So that's our product rule done. Now we're going to have to apply the quotient rule to this. Now our quotient rule, if you remember, is given by v du by dx minus u dv by dx, all divided by v squared. So to apply that, that's our u and that's our v. So v first, which is y, times the differential on top, which is 12x, minus u, 6x squared. I'm going to differentiate y. Now we differentiate y with respect to y, you get 1. But remember, we have to bung in that dy by dx next to it. And that's all divided by v squared. V squared is y, which, sorry, v is y, so it's going to be y squared. And that's all equal to, differentiate the constant, it's 0. What I'm going to do is I'm going to rewrite the product rule and the quotient rule in blue, a little bit to the side, because it's in the way a little bit. Okay, so we can simplify this then. This gives us 8xy dy by dx plus 4y squared plus 12xy minus 6x squared dy by dx all over y squared equals 0. Now, we could try and sort that out in terms of dy by dx, but there's no real need, because the question says find the value of dy by dx at the point 1, 1. So if we substitute, it's going to give us much easier terms to work with. So let's do that. So at 1, 1, we've got 8 dy by dx plus 4 plus 12 minus 6 dy by dx all over 1 is equal to 0. Simplifying, if we leave the dy by dx's on the left hand side, you got 8 minus 6, So we got 2 dy by dx is equal to, and you got 4 plus 12 is 16, so we got minus 16. So dy by dx is equal to minus 16 divided by 2, which is equal to minus 8. Good. So it's not too bad. You just got to be more familiar with your product rule. So use your product rule and your quotient rule. Okay. If you feel you have to break it up and do them separately, you can. I think it's better if we maintain the integrity of the equation, but you can do that part first and then do that part as a quotient and then put the two back together again. But I think this is the best way. So hit pause, copy the example down. When you're ready, hit play and we'll look at one more example. So with this example, we've got find the gradient at the point 1, 1 when e to the power of 2x log of y is equal to x plus y plus 2. So e to the power of 2x and then y is equal to x plus y plus 2. So what we're going to do is we're going to have to do this term as u and v. So we're going to be using the product rule again. I'm just going to switch to a blue pen to write on the side here. The product rule, which dy by dx is given by u dv over dx plus v du by dx. Okay, and switch back to normal red. Right, so in this product, that's our u. So to differentiate by the product rule, we've got to write u, e to the power of 2x, and then differentiate v, dv over dx. Differentiating log of y gives us 1 over y. But remember, we have to write dy by dx next to it. Plus, this time we write log of y, which is v, and then differentiate e to the power of 2x is 2 e to the power of 2x is equal to differentiate x with respect to x is 1 plus differentiate y, you just get 1, but remember we've got to write dy by dx times that 1, and you differentiate constant, you get 0. So that's that. Let's just simplify. So we have e to the power of 2x over y dy by dx plus 2 e to the power of 2x log y ln y is equal to 1 plus dy by dx. Now we could rearrange as it stands, but we don't need to because we want to find the gradient at that point. So we can say at 1, 1, sub in the values, e to the power of 2x becomes e to the power of 2 divided by 1, which is just e to the power of 2 dy by dx, plus 2 e to the power of 2 times log of 1 is 0. So we're going to multiply that by 0, so that's going to disappear. Is equal to 1 plus dy by dx. So simplifying, we've got e to the power of 2 dy by dx. This is gone because it's times 0. That's going to be equal to 1 plus dy by dx. Collect the dy by dx is on the left hand side. So e to the power of 2 dy by dx minus dy by dx is equal to 1. Factorizing, e to the power of 2 minus 1 dy by dx is equal to 1. So dy by dx, to conclude, is equal to 1 over e squared minus 1. So again, we've had to use the product rule, just as it is there. So this will help us actually practice the product rule without having to write things in terms of u and v. If you need to though, do it. Okay, so hit pause, copy the example down, and I've got some questions for you to complete. Okay, so I want you to start at question 3 up to 11. Good luck.